Okay, before that, I request every one of you to open a new tab and type joinpd.com and type this code MVFDDU. Those who have joined this session, please do join that joinpd.com also. So directly you can answer there. Okay, the code is I will repeat again. The code is MVFDDU. So even though you miss now, you can see it on the top right here. So MVFDDU. So
Yes,
today
sir.
we are going to solve 5 to 6, precisely 6 problems, which are related to week 8 graded assignment. So we'll start one by one. So the very first question is, let x1, x2 to x100 be independent, identically distributed random variables. So here you have to understand that these are IID samples. So IID, independent, identically distributed random variables, each with expected value 3 and variance as 9. So variance is given. Please be on mute, everyone. I'm getting some noise. Okay. So expected value of x1 is 3, x2 is 3, likewise. So this is what it means. And also we have given you the variances. Variance of x1, variance of x2, variance of x3, all are equal to 9. So now what we ask you is, you have to approximate the probability that the sum of these random variables x1 plus x2 plus x100 is greater than 100. So you have to approximate this probability. The event is, if I look at the sum of these 100 random variables, my sum of 100 random variables greater than 100, I want the probability. We cannot find the actual probability, so that is why we are approximating the probability using the central limit theorem. So CLT is basically used to approximate probabilities. So it uses an approximate value of the probability. Now here we have asked you to write your answer in terms of FZ. So it's like standard normal CDF. Okay, if you got FZ of -2, just type FZ in brackets -2. So if you got FZ of 2, FZ bracket within the brackets 2. So like that. And I hope everyone know what is CLT, central limit theorem. Yes, no? Am I audible?
Sir,
Yes, sir.
like till the people who know are solving, can we discuss it once?
Yeah. So
Like, what is CLT? Questions we can discuss later, but CLT as
Yes, sir. Once you please explain CLTs.
So what is CLT is basically central limit theorem. Okay. So this particular theorem basically gives us whatever distribution you have with some mean and some variance. You can actually approximate the distribution to standard normal. So whatever the distribution may be, we don't even worry about whether it is discrete or continuous or whether it is some vague distribution. We don't know whatever it is. But if you know that distribution is having some mean, some variance, so after computation. So you consider all the data points, all the population data points, and you compute the mean, and you can compute the variance also. So that will be the mean of the distribution and variance of the distribution. So if you know these two, and irrespective of the distribution, you can actually approximate that particular distribution to standard normal distribution, is what central limit theorem is. So let me stop this presenting and I will just open.
Sir, this session is not being live streamed.
It's not being live streamed, that is why I'm recording. So it will take one day, maybe tomorrow morning you will get the recording. Just 1 second.
Sir, when we'll have that week 6
Sir,
to
like
8 notes, sir?
if this session would have been
Hmm? When are you? Someone asked something.
Yes, sir.
When?
Yes. Up to week 5, we have got the notes, isn't it, sir? Some which
Week
includes
6.
some
Yeah,
very
yeah,
very nice important points but
yeah, yeah.
week 6 onwards it's not there, sir.
You are asking about book, I suppose.
Yes, sir. Yes, sir. Anyhow,
Uh,
I'm writing the
practice.
notes and I'm taking all the points what you are teaching in these live sessions. But in addition to that, the first 4 weeks, I mean, the previous ones, the concepts were very helpful, sir, in that quiz one.
that is being under review. Okay, so it will take
Okay.
some time.
So will it take time, sir?
Some time.
Okay. Okay, sir. Thank you.
Okay. So we are discussing central limit theorem. So in short, it is called as CLD. Okay. So what this CLD tells us is, if you have enough samples from a distribution, so this n should be sufficiently large. Sufficiently large means in our numerical terms, n should be greater than 25 in some books, and in some books they will say n should be greater than 30. So whatever it may be, so at least it should be greater than 25. That means you should have at least 25 samples from your distribution. So whatever the distribution is, IID, so let's say X. So X is following some distribution. We don't know that distribution. And out from this random variable, from this distribution, we have pulled out some more than 25 or more than 30 samples. Now you have decent enough samples to approximate your distribution. So if you have this, and you can, if you know this mu, which is the expected value of X, so the distribution mean. So this is the distribution and these are the samples. So, okay, treat it like this. Out of all the population in India, you just randomly pick some 100 or 200 people. So picking those 100 or 200 people is what the samples are. And what is my distribution? My distribution is all the people in India, and I am choosing randomly one person. My random variable X takes some name of, not some name, the weight of the person or something. But my population data is whole population of India. But in order to check the average weight of a person who is living in India, so I can't go to each person and I can check the weight of each person. And like this, I have to check for 130 crores. 130 crores, right? Now it passed it. That too. Okay, any figure. So I can't go to each and every person and I cannot take the weight of each person and then compute. I will add all those things divided by the number of people living in India. So it is very difficult to do. We don't say it is not possible, but it is very difficult to do. But what we can do is we can randomly pick from 10 people from Jammu, 10 people from Rajasthan, like this. If 10 is not enough, we will pick 100. So 100 is sufficiently small enough than the total number of people in India. So picking those kind of people are called samples. Smaller portions of population is what samples. Okay. So if we have taken some random samples out of this distribution population, and you know the population mean, so these are in week 7 and week 8, we assume that we know what is exactly distribution is. Okay, we know what the distribution is and the means of the distribution and all the parameters of the distribution we know in week 7 and 8. So that is what we are going to learn in step by step. So in week 9 and 10 we will see what if the parameters are unknown, but in week 7 and week 8 just uh, be clear that we are assuming that we know the population mean and population variance, which are nothing but the parameters of the distribution. Okay, if we know that, can you compute the probabilities or can you approximate the probabilities? So for that, answer is yes. So how it is yes? Because whatever the distribution you have, you can approximate the distribution to standard normal distribution, and once you convert to standard normal distribution, we know how to compute the probabilities. So this is the step. So this is later part of the portion. So these are the things we know. We are assuming, these are our assumptions, that we know mu and sigma square, which are parameters of the population. Okay, so these things we know. So that is known. Okay, so once you know this of any population, once you know this, in this week 7, what we are going to do is we are going to compute or approximate probabilities of certain events. So certain events, whatever it may be, now itself we have seen a question, right? It's like, it may be event like this. Of certain events, we are going to just compute or approximate the probabilities. So how we can compute is using weak law of large numbers or CLT. We will compute or approximate the probabilities. And also we will study few properties of population and the samples, sample mean, expectation of sample mean, expectation of variance, how they are related to the actual population parameter. So understand this. So week 7 and 8, we are only worried about this from here to here. And there is one more thing. The next step we are going to learn is this. So what if they are unknown? So if they are unknown, we will try to predict, or we will try to predict what will be the approximate possible value for mu and sigma square. Then we will compute and approximate probabilities of certain events. So if it is unknown, we will try to find this mu and sigma squares using samples. Okay, we will see it in week 8. So right now you don't need to worry about this. Right now this is true. This is known. Mu and sigma square are known. Okay, if you okay, right now mu and sigma square are known. What CLT is, if I have some sufficient enough samples which are coming from IIDX, and also if I know the expected value of x is mu and variance of x is sigma square, then you see this a new random variable which is a function of these samples. It can be any function. So it can be between just the sum, or it can be this. So this is y1, this is y2, or it can be the mean.
It is just f of x1, x2, x up to xn, right?
If it's just a function of these samples.
Yeah.
Y. Okay. If that is the case, any function. Now this y1 minus expected value of y1 divided by standard deviation of y1 will follow standard normal 0. So if you remember in week 3 or week 4, if we have standardization, so standardization, if you remember, x is a random variable, any random variable with some distribution. So then x minus expected value of x divided by standard deviation of x will follow normal 0, 1. So just recall. So in week 3, I suppose. So a term called standardization, there professor has discussed, if you have any random variable x, which has some mean mu
Yes,
and
sir.
some variance,
Yes,
x
sir.
minus
There,
x.
sir, we only standardized. It was given x is already a normal variable, sir.
And the first
Normally
question of
distributed
graded
value.
assignment was related to this only.
So if x is a normal, yes, the standard. If x is a normally distributed random variable, then you can do this. Okay.
But if it is not normally distributed, so here y1 is not necessary to be normally distributed, is it?
See here, whatever the functions we talk about, they are all normally distributed functions. So this
So
sum
that
of
should be given then, na, sir? You were saying any function, so
But sir, as n increases, it will approach to
ha
n
ha
not
ha
normal
ha.
0 1. It is not given that it is approaching that normal. It is
Sir?
approximating normal.
Hmm.
Sir, in CLT, the
Hmm.
denominator will be square root of n into sigma, right, sir?
That is why I didn't bring any n or sigma or anything. So y1 minus expected value of y1 divided by standard deviation of y1 will follow normal 0 1. And if you compute for this, if you wanted to normalize this, then y2 minus expected value of y2 divided by standard deviation of y2 will follow normal 0 1. So you can compute using, now you see expected, what will be the expected value of y1?
expected
value
value
of
of x1
x1
plus
plus x2
expected value of
plus
x2.
Expected value of x2 plus and so on, expected
So
value
here
of x.
y2 is sample mean.
Y2 is sample mean.
Okay.
Okay. So you can derive those things. You don't confuse
Sir,
with root and sigma or anything.
sir, one question.
Hmm.
Sir, y1 and y2 are giving insights for a sample only. These are the function of sample.
Hmm.
So how y1 minus expected value of y1 upon SD of y1 is giving an insight to the population?
See, that is what we are going to do, right? You can only take sample and you will predict the distribution of
So
population.
we have to take numbers of samples then.
Number?
Many number of samples.
That is sufficiently enough samples. I told you, right? N should be sufficiently enough. You shouldn't pick like 2 or 3.
Then sir, how will we determine how much is sufficient?
The researcher said that at least you should take 25 or 30 samples, at least. Okay.
Okay.
Hello, sir.
Hmm.
Sir, how can I find out expectation of y2?
You can compute, right? Let's do y1 first, and we will go to y2. So y1 is basically x1 plus x2 plus and so on xn. So what will be the expected value of y1? So it's basically expected value of x1 plus x2 plus xn, and using the linearity of expectation, so you can write expectation of x1 plus expectation of x2 and so on expectation of xn. And we have given that x1, x2 and so on xn or IIDs of x.
Mu.
So
All have mu.
whatever the expectation of x1 will be equal to expectation of x. So these all will be mu plus mu and so
N
on
mu.
mu. So it will be n mu.
N mu.
So next comes variance of y1. So what will be the variance of y1?
So they are independent. We can add directly.
Right. So they are IIDs. So we can do variance of x1 plus variance of x2, variance of xn. So x1, x2, xn all have same variance that x has. So all will be n times variance of x. And variance of x we know n sigma square.
Sigma square.
Now, what will be the standard deviation of y1? Root n sigma.
Yes, sir.
Correct?
Yes.
So what I said, y1 minus expected value of y1 divided by standard deviation of y1 will follow normal 0 1. So just substitute y1 minus expected value of y1 is n mu divided by standard deviation of y1, which is root n sigma. So this will follow normal 0. Okay. And we have also talked about y2, which is basically the sample mean.
But then sir, how do we go from y1 to y2?
So y1 to y2 is basically, see, you see this is y2 is basically y1 divided by n, right?
Yes, sir.
You can go from here, right? What will be the expected value of y2 in terms of y1?
Expected value of y1 by n.
1 by n into
Okay.
expected value of y1.
Yeah,
And what
that
will be
is
the
mu.
variance of y2?
Expected
1 by
value
n
of
square into variance.
By n
variance.
square
Yeah.
variance.
So it will be basically, if you write y1 by n, so 1 by n is a constant, you can bring it out, so it will be 1 by n square, it will be squared if you bring out inside
Variance
of
of y.
variance. Yeah.
Yeah.
So it will be variance of y1. So
Okay.
here it is mu by n, here it is sigma square by n square. So simple, y2 minus mu by n divided by, sorry, so it will be, if I compute the standard deviation of y2, it will be sigma by n. So this will be sigma by n.
Okay, sir.
So this is how it is. So now it will be like ny2 minus mu divided by sigma will follow normal 0. Okay.
Clear, sir.
So forget about whether it is mean or whether it is sum. Okay. So usually we will be asking you about sum or mean. So either of it. So
Any general function we can approach this way.
any general, even though if we give any general function like x1 into x2 into xn, so for that it is very difficult. Okay, if we have given y3 as something like x1 plus xn by 2, simply x1 plus xn by 2.
Yeah.
Okay. Or
But sir, it should be given that
Ah.
x1, you were saying x1, x2, x3, xn. Let's say that. So, theoretically, it's very difficult to find out its values, but do we know that it will be normally distributed for sure?
so that is what this theorem says.
So I do not understand. The theorem says that this y1 minus expected value of y1 divided by standard deviation of y1 will be normally distributed 0 to 1. But that's only if y1 is normally distributed itself, right?
See,
I'm asking, will y1, will every function of x1, x2 up to xn will be normally distributed? How do we know if it is normally distributed or not?
x1 to xn are not normally distributed. If you increase this n, or if you take more and more samples out of the distribution, if n is going to infinite, you can treat it like that. So if n is becoming larger and larger and you are having more and more samples, then I guess sir has used moment generating function. The moment generating function of this one, y, which is xn divided by root n something. So this particular y, this random variable y, will slowly start tend to follow normal 0
distribution.
sigma square.
Okay.
Okay.
But that is true. For moment generating function, it is true. So it is true for every function. Can we say that?
Any
Yes, sir.
distribution, so it will slowly, whatever the function we have, so if it is just divided by n, divided by root n or divided by n, both will
So
go
constant
and
value.
approach. So from root n, professor has proved that this moment generating function of y is same as the moment generating function of normal 0 sigma square.
Okay.
So it will tend to
Sir, can we say it like if we take different sample means and the distribution of those different sample means for a sufficient value of n will form a shape of normal distribution?
See,
Yeah, that's what they are saying.
yeah. See, you know the normal distribution curve, right?
Yes, sir.
So how it will be? So usually it will be like this, right?
Symmetric, sir.
Symmetric around the mean, and mean may be at mu, and our standard deviation may be sigma. So usually the curve will be like this only, right? Normal curve. So now whatever the samples you pick, So once you do a sampling, you will have some values x1, x2, x3, and so on, some x10. So you plug in those values here. So here, here, maybe here. So you find the mean of it and you find the variance of it, and you can correspondingly draw a curve by having this 10, not 10, 100, let's say 100. So you keep 100 samples. So 100 sample values, So after 100 sample values, you just plot it on this plane. And once you plot it, you know how to find the mean, and you know how to find the variance also. So once you have the mean and variance, so that is the advantage of normal. So you can approximate that this follows normal mu and sigma square. So with mean mu and sigma square, which you got mean from this and the sigma square also from this. So just plug in those values and you just simply say whether if it is greater than mu, you just plot it on the right side. If it is less than mu, you just plot it on the left side, and you will somehow predict. You will somehow draw. Okay, let us say the value of this is this much. Other one is this much. Other one is this much. This one is this much. So like this. So you might get this, or sometimes you might get like this. So you studied best fit, right? So this, and mean you might have like this. So now you have to slowly approximate this data into normal distribution data. That's it. You will take this curve, you will slowly increase the standard deviation or mu, and you will slowly come and plot. You will approximate, that's it. So this what we can say, we can fit whatever the data you have, you can fit this curve, this kind of curve around
Sir,
the mu.
all these data are sample means, no?
Whatever the function.
Whatever you see from a population, once you pick a random sample, you are randomly picking some value.
Yes,
So
sir.
that particular value is coming from the distribution, and once it comes out, it will be a sample in your hand. Okay, now that is a sample from the population. Now you have seen one observation, one instance of the whole population. Okay, x1,
Yes, sir.
this x1 represents the first sample you pick out from the observation, and you can pick any sample. Sorry, you can pick anything. So if I talk about an example, you have a pot, okay, and there are some 100 balls inside it with numbering 1, 2, 3, and so on, 100. Okay, so if I pick any ball randomly, okay, the number on that ball will be a random variable. Yes or no? So
Yes,
you
sir.
can draw 1 or 2 or 100. But once you have drawn, so once you have drawn it from the pot, you can see the number, right?
Yes, sir.
That will become a sampling. So once you have opened, so that is the difference between small x and capital X. Capital X represents a random variable, and small x is actually a value taken by this random variable.
Sir, I have one doubt.
Hmm.
So say for example, I'll go to that example of average weight in India. So say for example, I take one sampling in which I've taken 1 lakh people's samples as weight. Okay. And sir, I take out the average, like I linearly add everybody's weight and then divide it by 1 lakh. And sir, how will this approximation be better than that one?
Better than which one?
So the linear, I linearly added them and took out an average. Then, sir, like that average will represent the mean of the population.
No, that average will not represent the mean of population. Whatever you have computed, it will be the average of one sampling. Okay.
Okay.
Okay. Like this. you have to do some 1 lakh samplings, 1 lakh samplings of 1 lakh people, or more than 1 lakh also, and you will get 1 lakh means.
Okay.
And if you take the mean of it, it will approximate, or it will come closer and closer to the mean of population.
Yes, sir. Yes.
Okay, so how do we get that is, see, this x1, x2 and x3 and x100, let's say. So once I have seen the sampling x1, x2, x3, x100, this is the first sampling, correct?
Yes, sir.
So x1 has taken x1, x2 has taken x2, x3 has taken x3. Out of all possible values of x1 can take, x1 has taken small x1 in the first sampling.
Okay, sir.
Okay, and in the second sampling, it may take something like y1, small y1. So it may not be x1 only.
Yes,
Right.
sir.
So the first person you pick for the first time, his weight may be 70. But if you are sampling for the second time, the person chosen for the first time may not have the weight 70. It may have, he or she may have different weight. So
Yes,
this
sir.
x1 takes values x1 or y1 or z1 or something else. So these are sampling, second sampling, third sampling. Okay. So how I can compute the mean of this? So the mean of this is nothing but the mean of this random variable,
Yes, sir.
right? Similarly, like this, if I know the expected value of x2, that will be the mean of all the possible values x2 can take.
Yes, sir.
Yes.
So like that. So this here also it is expected value of x100. X100 will give us the expected value of this 100th sample. So 100th person you are going to choose, it will give you the expected value of that 100th sample.
Sir, then x1 means first sampling value, x2 means second sampling value, like this.
Are you talking about capital X or small x?
Capital X.
So capital X are samples. So sampling is one instance of picking the samples.
Yes, I understand. Capital X1 is the set of all fast sampling values. Am I right or wrong?
No. Capital X1 is a random variable that takes values equal to the first sample.
Values equal to the first.
So see here,
Yes.
if in this pot, if there are 100 numbers, 100 balls, okay, if I
Yes.
have to pick one ball out of it,
Same color. All the ball has same
all the
color.
balls are same color and
Okay.
it's numbered. Okay, they are numbered 1, 2,
Okay.
3, 100. Okay, and I represent my x1 as the number on the ball. Okay, now tell me, capital X1 is a random variable or is it a constant?
Random variable.
Random 1 to 100.
One,
Anyone can I pick?
any one can be taken by this x1, capital
Yes.
X1, right? But once
Yes.
if I pick, so I have you are standing in front of the pot and you have kept your hand inside and you pick the ball outside and you have seen the number on the ball. Okay,
Yes. Yes.
so let it be 7. So that will be equal to x1, which is 7. This is one instance of your sample. So your capital X1 has taken value 7 and that 7 is represented as small x1. So now this is a constant.
Sir, if I next time, if I pick x1 is equal to 9, say, x1 is equal to 9. Second time in second day, I just pick first sample and it is 9. Then set of 7 and 9 is capital X1 or
See, capital X1 can take any value between 1 to 100.
Okay.
So that will be a random variable. Random sample. Okay. So the sample
what if-
means you are
So
picking.
what, so what if we
Huh?
take 3 balls at a time? So what is the x1 there?
You can treat it like x1, x2, x3. So you are picking, if
Okay.
you are picking 3 balls, see, this is a random variable. You have to define yourself.
All 3 are random.
That
Yes,
means
yes.
capital X1, capital X2, there is no relation about first sample value, second sample value. I think there is no relation. Now, X1 can take 1 to 100, X2 also can take 1 to 100.
Hmm. Okay. These are random variables. X1, X2, X3 are random samples. So random samples, which means they are each one of them are random variables. Okay, understand that. And if I talk about sampling, first sampling, second sampling, third sampling, first sampling means I have performed the experiment and I have seen the sample values. So once I have seen the values, the set of all the values will be the sampling. Okay. And likewise, I can do the second sampling, third sampling, fourth sampling, and fifth sampling also. And correspondingly, x1 takes values x1, y1, z1 or something else. And it can take x1 in the fourth sampling, it can take the same value also. We don't know. Okay. But if I wanted to talk about the expected value of the possible outcomes of capital X1 is nothing but expectation of X1. So even if it is 100 samplings or 1000 samplings, even if I look at 1000 samplings, all the values, all the 1000 values, if I see, if I wanted to compute the average of those 1000 values or 1 lakh values, that will approach to the expected value of X. So this is nothing but you treat it as a single random variable. So this is like X1 is having some distribution with some possible outcomes in the range. So if I talk about the
Yes,
expected
they're
value of
identically
X1,
distributed. Like you're picking just different samples. You're just calling them 1, 2, 3. Right? There's nothing new.
right. So there in week till week, that is what I said, till week 4, week 5, it's just the basics we learned. So what is a random variable, how to look at a random variable, and what is the difference between random variable and a constant, and what are the possible values that random variable can take. If these are the possible values that random variable can take, what is the expectation of the random variable, what will be the variance of that random variable. So these are the things we have seen. Now here, each of the sample is a random variable. So we are collectively looking at hundreds of random variables, thousands of random variables at a time. And we are also looking at functions of these random variables also, which we have seen in week 3 and week 4 also. Functions of 2 random variables, 3 random variables, x1 plus x2, x1 times x2. So that is why. So we don't say till week 6 it is not important. Week 6 is always, till week 6 it's always be base. It will be underlying below the ground. So we will always use it at any point of time. Okay.
Sir,
So yeah,
syllabus of quiz 2 is 4 to 8 or 1 to 8?
see, it's 1 to 8, man. But more, we will ask questions based on week 5, 6, 7, 8 contents only. But anyway, they are also connected to weeks
Okay,
5,
concepts
6.
are related.
Concepts are related. So we say weeks 1 to 8, but whatever the question you see, that will come from 5, 6, 7, 8.
Before quiz, there will be a revision session, na?
For 7 and 8. 5 and 6 we have already done, right?
Yes, yes. Okay.
So okay, ultimately let's come back and let's see this thing. So what CLT says is, if I have any distribution and enough samples from that distribution, and also if I know the expected value of the distribution and the variance of the distribution, then whatever the function I have from these samples, I can approximate that function random variable to standard normal using this. So that function, whatever it is, random variable y1 minus expected value of y1 divided by standard deviation of y1 will follow standard normal 0, 1. Okay, use this now and solve that question.
Sir, can we see a few problems regarding this CLT?
Huh. See, anyway, this session is all with us.
No, sir. Actually, there was this one exercise activity after the lecture where sir introduced CLT. That question set I was not able to understand completely. It went.
Okay, we will do couple of it then after this question. So now using all those things, just try to do this. So I have given some x1 to x100 IID samples, and I have given you the expected values of each of it and variances of each of it. And using CLT, approximate the probability that x1 plus x2 plus and so on x100 greater than 100.
So, sir, in the exam, we will be given the CDF of standard normal distribution.
We will give you. If the values are required, we will give you.
And in the grade assignment, it is not given. So we have to consult it somewhere or what?
Yeah, you can get online Z tables, right?
Okay.
So
What
now
is
that you
Z
can,
score, sir? I do not understand. The tables are mostly in terms of Z score.
the tables are in terms of Z score is the value of the corresponding point, right? Yeah, that is it.
Like if I am trying to find FZ of something, that's something.
Nikita madam had shared a table in the last class
Hmm.
for CDF of standard normal.
Okay. So can you share that here again? Is it
I'm not
possible to?
having access to my laptop. Actually, I'm on a mobile.
Okay.
Uh,
Okay. We will. I will ask Nikita to share it. Okay. Or else, see, you can get it through online, man. There are many Z
There
tables.
are calculators also, but they have to be reliable, no?
They are reliable, right? Calculators are reliable to compute the values. See,
It should be from a reliable source, no? So,
Acha.
so how to enter the answer of this number, sir? You have to see the.
You if your answer is fz of -2, that type fz in brackets within the brackets -2.
Okay, sir.
Just a second.
Sir, when these notes will be available in the portal, because tomorrow is this note. Today's.
This all with the slides, you will get it today night itself. Maybe the session recording you will get it in the tomorrow morning.
Okay.
Okay.
Slides. Okay. Tomorrow the graded assignment submission last date.
That is why we are having solve with us today, or else we would have had tomorrow. So these time sessions are not being YouTube streamed directly, right?
Yes,
So
please
that
be
is
sure
yeah,
that the
yeah.
slides are available by today
Sure.
night.
Sure.
Sir, I've shared one of the table in the chat box. Can you tell me how to read it? Like there are two row and columns. I understand the column thing, but do not row thing. What does that say?
See, Okay, let me share. And so most of you don't know how to read this, is it? Just a second, let me share it. So is this done? Let us do one question at least. Okay. Then we will do that.
Yes.
Okay. So how do we do this? Basically treat this x1
We
plus
just
x2.
take y is x1 plus x2 plus up to 100.
Correct. Let me see what the 10 people gave. So 1 minus fz of minus 20. Okay. Minus 20 by 3. Yeah, that is correct. So what we have is, we know we have the expected value of xi and we have the variance of xi also. So in order to approximate probability of x1 plus x2 plus x3 and so on to x100 greater than 100, let us say this sum is equal to some y or s100. So here we have taken it as s100. So this s100 is also a random variable. So you can take it as y. Nothing. There is no change. But the main thing is this: using CLT, whatever the random variable I have as 100 or y, so S100 minus expected value of S100 divided by standard deviation of S100 will follow normal 0, 1. This is what CLT says. Now we have to compute what is the expected value of S100 and what is the standard deviation of S100. The expected value of S100 is nothing but expectation of x1 plus x2 and so on x100. So this will be expected value of x1 plus expected value of x2 plus expected value of x3 and so on expected value of x100. So each of their expectation is equal to 3 and there are 100 like that. So it will be 100 into 3, so which will be equal to 300. So similarly, variance of S100 will be variance of x1 plus x2 and so on x100. And as they are IIDs, so I can write it as sum. So variance of x1 plus variance of x2 plus variance of x3 and so on. So each of the variances are also equal to 9. So there are 100 of it. Therefore, it will be 100 into 9. It will be 900. Now you see we have to compute probability that S100 is greater than 100. Now for that, what we have to do is, we know that probability that S100 is greater than 100. Now we have to convert this S100, so this is a random variable, to standard normal random variable. So how we can compute? We can subtract expected value of S100 divided by standard deviation of S100 we can do. So that is what, on both sides. So once you do on the left hand side, you have to do on the right hand side. So if I do that, we will get S100 minus 300. 300 is the expected value of S100 and divided by square root 900. So square root 900 is square root of variance of S100, which is the standard deviation of S100. So it will be square root of 900 greater than. So whatever we have done in the left hand side, we should do it on the right hand side. So we have done minus 300 divided by square root 900. So the same thing we will do here also. Minus 300 divided by square root 900, which will be equal to 30. So now we know that this has 100 minus 300 by square root 900 will follow standard normal 0, 1. So you can replace this with capital Z. So now Z is a random variable which follows normal 0, 1. And we have got probability that Z greater than minus 200 by 30. If you cancel it out, it will be minus 20 by 3. So probability that Z greater than minus 20 by 3 will be equal to 1 minus probability that Z is less than or equal to minus 20 by 3. So probability that Z is less than or equal to minus 20 by 3 can be written as, in terms of CDF, we can write it as Fz of minus 20 by 3. So the answer will be 1 minus Fz.
I have not understood the last step, sir. I have got till the probability of S100 minus 300 in the step above. Till that it is clear that we are standardizing both on left and right side. But where did this Z came from?
So this S100 minus 300 divided by square root of 900 is a random variable, right? So now this is this random variable will follow normal 0. So treat it like a random variable. Even this is also a random variable.
Yes, sir.
Okay. So instead of writing all these things, we just replaced it with Z.
Okay.
Because Z is usual denotation for standard normal random variable. Okay.
Okay, sir.
Okay. Yeah.
Right.
So from there you will get this.
Sir,
Hmm.
sir, the z-score it's minus 20 by 3, sir. So it's around minus 6 point something. So usually in the z-score table, the values are from between minus 4 and 4.
Okay. Let
So
me
what should
open
I do?
the Z table and let me
Sir, before that, could you please show the question? What was the question here, sir?
here.
Yeah.
This is the question.
Okay.
Okay.
Yes, sir. Got it.
Okay. Let me show the second question and people try this. So there are again 100 random variables which follow IID normal 0 2. Okay. Now you have to approximate using CLT. Find the probability that x1 square plus x2 square plus and so on x square 100 x 100 square greater than 220. So for this you need one thing. So if x1 follows normal distribution, x1 square will follow
Gamma distribution.
gamma distribution. Correct. So that you have to that you should know. Okay. Once you know that, you can compute this. Okay. And also one more thing you should know, sum of n gamma random variables will follow gamma. Again gamma, it will be gamma only. Okay, but the parameter will change, but it will be gamma only. Okay, let me write those things also. I should have written this here itself. So these are the two things you require. So if x1, sorry, okay, I will write it in x terms. If x follows normal 0 sigma square, then x square will follow gamma 1 by 2 comma 1 by 2 sigma square. Okay, this is one thing. This is the first thing. And the second one, what you require is, if I have x1, x2 to xn, which are IID gamma alpha beta, then x1 plus x2 plus x3 plus and so on plus xn, this random variable will follow gamma n alpha beta. Just check the correctness. N alpha beta is what I hope. N alpha beta. And if I just wanted to combine these two, you just combine and you just try. Okay. So the third part is the combination of 1 and 2. So if I have x1, x2 to, so whatever the question is given, xn, follow IID 0 sigma square, then x1 square plus x2 square plus xn square will follow. So I will give it to you. It will follow n by 2 comma 1 by 2 sigma square. Okay. So we have combined these two things. That's it. So this is the thing you require.
Yeah, can you please show the second point?
I didn't understand.
Second point, second point.
Second point.
Can you please show?
Okay. These are the two things you require. So people who are in join PD, just try to solve that question number 2. Meanwhile, I will just go through this Z table. How to go through the Z table. Okay, those who don't know how to go through or how to read the values in Z table, this is how you have to read. So this table is given from minus 3.4 to plus 3.49. So you see this, the row thing, so this represents capital FZ of minus 3.400. So this particular 0.0003 is the value of capital FZ of minus 3.4. And if I wanted to compute like this, it will be minus 3.41. So the value for FZ minus 3.41 will be, so this is the 100th, so second decimal place. First and second decimal places. Okay. So minus 3.41. So FZ of minus 3.41 will also be equal to 0.0003.
Sir, I think it will be minus 3 point, like reduce one, like minus 3.3, and in between now you are increasing it. It's negative. So I think it will be 3.9 maybe.
Right. Just hold on.
For positive that will work. Just adding.
So this is complete table, right? Okay. So this is minus 3.4 plus 0.01. So these are positive values and these are negative values. So this particular 0.003 represents the value of FZ of minus 3.4 plus 0.01. Okay. So something like this you can see. If I want to compute FZ of minus 2.95. Okay. So you have to come to minus 3.0 table. So FZ of minus 2.95, you can write it as minus 3 plus 0.05. So once you write that, you come to minus 3.0 table and go to 0.05 column. Now this particular 0.0011 represents FZ of minus 2.95. Okay, minus 2.95. This is minus 2.95 because minus 3 plus 0.05 will sum up to minus 2.95. So see the corresponding row and column value. So that will be equal to 0.01.
I think that logic is not correct. It will be minus 3.05.
Minus 3.05.
Yes, sir. It should be minus 3.05 because in the first row you have told that minus 3.4 plus 0.01 is minus 3.39.
No, if you add negative to positive, it will reduce now. Minus 3.4
No.
plus 0.01.
These columns
That should be minus
just
3.3. Minus 3.99.
Just
That's what Sir said. Now after adding,
columns
it will
are just
reduce.
indicating decimals only. Columns are indicating decimal in front of minus 3.
Okay. 3.0. You mean that in the leftmost column, these are the negative values and we are adding something positive to it. So we have to create every number adding these negative and positive values.
No.
This 0.05.
That is just decimal in front of additional decimal in front of minus 3.0.
No. If that is the case,
value of any cell represents row plus column.
See, then in that case, just a second. Yeah. Values are decreasing, right?
Yes, sir. If we check the case of minus 0.0, so if we add 0.5, it's not becoming 0.05 value.
Okay. So what I suggest you is instead of going to the whole table, if you learn one side of the table, you can get the other side also, because it is symmetric around mean. Okay, if you are that confusing, don't go to the negative values of this. So basically whatever the later person said is correct, because you see in the table the value, if you go to the right side of the table, the values are decreasing. So from 0.0010 to 0.0009 and so on to 0.008 and 0.007. So the probability will decrease if we move left side only. Okay, so don't confuse with that. If you want the value of minus 2.95, then
Okay,
do
you mean
1
to say that
minus
get
of
the value of plus 2.95?
plus 2.95 and you subtract 1 from it. So you know how to find 2.95. 2.9 and 5 you go in the fifth column. It will be 0.9984. So this is 0.9984. If you subtract 1 from it, you are going to get 0.0016. So that will be the value of minus 2.95. Minus 2.95, it should be 0.0016.
Yeah, sir, correct.
Me?
Okay.
So I just used a calculator, actually Desmos, to plot the function. What we have to do is we have to add the corresponding value for example, we want to calculate fz for minus 2.3. Then we can split it as minus 3.0 plus 0.7, and then we can first check in the row of minus 3 and then for the column for 0.7. I just used Desmos to verify the values.
0.7 we don't have a column, right? We have column for 0.07.
Okay, 0.07.
See, simply this represents the second decimal place. That's it. So this is 3.40. This will be 3.41. This will be 3.42. Like this. This will be 3.49. So this is almost minus 3.5. So fz of minus 3.5 value will be less than fz of minus 3.4.
Okay.
So that is why the value is decreasing from 0.003 to 0.0002. Okay. So it will decrease. This is just the second decimal place value. So minus 1.75, if you want the value of minus 1.75, you simply do minus 1.7 and then go to the fifth value.
Okay.
Sixth value. So it will give you the minus 1.75 value, which is 0.04. Okay. But if you don't want to look at minus 1.75, you look at 1.75. So 1.7 and 5. This is 1.75, which is 0.9599. So 9599, 1 minus 0.9599 will give you the value for fz of minus 1.75. So it will be 0401. So 0401.
The first row for minus 3.4, all the values are same. For 0.00,
So there is
for
no much change. That means there is no much change. That is already 1 by 10 to the power 4 value.
Okay.
So the fourth decimal place is being varied. Okay. So if you go after 3 standard, see, this is actually the standard normal, means it is normal 0, 1. The standard deviation is 1 with mean 0. Okay. Minus 3.4 means it's already 3 standard deviations away from the mean. So almost that will be equal to 0. Okay. So this is how you read. So the values on the columns represents the second decimal place. That's it.
So to go to the point where we started, how do we compute fz of minus 6.6? If we see the previous problem, we got minus 6.6.
Minus 6.6 is way lesser than minus 3.4, right?
No, in the previous problem, if you see, we got the value as minus
It
20
will
by
all
3.
okay. It will almost be equal to 0.
So do we have to, whatever goes beyond this table, do we have to take it as 0, sir?
So that is what it, even minus 4 itself, it will go to 1 by 10 power minus 1 by 10 power 6 or such. Okay, you can treat from minus 3.5 or more lesser than minus 3.5, you can treat it as 0.
Sir, so if you look at the positive side of this table, the other side, anything above 3.9 is very close to 1. So we can take anything above 4 or 3.9 as approximate to 1.
3.5 above, it will be approximated to 1.
Okay, sir.
3.5. Yeah. So yeah, that is what you have to understand. It's 3.5 or minus 3.4. They are 3 standard deviations away from the mean. So you know the three standard deviation rule, right? Do you guys know? 66% of the data will lie within the first standard deviation. 95% will lie within the 2 standard deviations, and 99.98 samples will lie within the 3 standard deviations. So what
Yes,
are the
sir.
probability that will come within 3 standard deviations only, from minus 3 to plus 3. So from plus 3 itself, you can see till plus 3 only, it is 0.9987. It is almost nearer to 1.
Would it be possible for you to draw the graph over here of what area
9946
is actually giving, which area it's been given by the table?
Plus minus 3 standard deviation is 99.46.
99.46.
Yeah.
Yeah. So it will give the left portion of the line.
Left portion, say for example, if it's 3, then it will be the whole up to 3 standard deviation.
No. Left side of that line. So if you are talking about minus 3, then left side of minus 3 line will give you the probability.
No, if it's positive 3?
Whole.
It's giving the left area, right?
Left area only. It will give the left area only.
We don't have tails in Z, right? It's only in T.
So if you are looking at, so 3 will be here somewhere. Okay.
So it's giving the area, whole of the area except the one to the right.
So the table will give you the area under this curve till 3.
Okay, thank you.
So like this. So this is minus 3 maybe. And left of minus 3.4 is here. So this will almost come to 0. So if you still go lesser than minus 3.4 or 3.5, it will almost be 0. Okay.
Sir, let us get to the question, sir.
I'm going back to the question. So I have given you 2 points there. So use those 2 points and evaluate the probability.
Done, sir.
Done. Okay. And 2 more points you require, the expected value of gamma distribution and variance of the gamma distribution. What is the expected value of a gamma distribution when the parameters are alpha and beta?
Alpha by beta, sir.
Alpha by beta.
Yes, alpha by beta, and the variance will be
alpha by beta square.
Alpha by beta square. Correct. So use those things also.
Smiley, have you crammed those formulas?
Have you? Have I?
No, I just opened the formula sheet in the dashboard.
See, these formulas and everything we will give you, we will provide you. Just like quiz 1, we will provide
Yes,
you.
I just opened the
whatever
formula
important
sheet
formula.
whenever the session is going on. That was provided in quiz 1. I have started opening it.
See, you can actually prove it. If you know the PDF of gamma distribution, I think professor has not given the PDF exactly. So if you have the PDF, you can use that integral x dot PDF of fx of x dx. You will get the expected value as alpha by beta. Only 5 people. See, whenever CLT comes into the picture, you should have only one thing in mind. Whatever the random variable is given to us, you have to find the expected value of that random variable and the standard deviation of that random variable. So function of random variable. So here the function is like x1 square plus x2 square plus and so on x square x 100 square. So treat this as a random variable now. So you have to find the expected value of this and the standard deviation of this. Subtract the expected value of this divided by the standard deviation of this. You will get something on the right portion, right side, and that you convert it into the CDF of standard normal. So usually this will be the trend. Okay. So let us move. Okay. So let us see the answer for this. 7 people has answered as 2.2392382 Okay, 1 minus of this is, I suppose. Okay, so the same thing, xi's follow normal 0 2. So if xi's follow normal 0 2, xi squares will follow gamma half comma 1 by 2 sigma square. So sigma square is 2 here, so it will be gamma half comma 1 by 4. So now I know the expected value of this gamma distribution, which is alpha by beta. Alpha is half and beta is 1 by 4. So half divided by 1 by 4. So that will be equal to 4 by 2, which will be 2. And sigma square, which is the variance of these xi squares, will be alpha by beta square. So alpha is half and beta is 1 by 4. So 1 by 2 divided by 1 by 4 whole square. So we are going to get 16 by 2, which is 8. Just a second. Someone asked anything? So someone raised their hand, is it?
Could you write, is the formula for variance written? It's alpha by beta whole squared or alpha by only
alpha
beta?
by beta whole square. Not whole square, beta square.
It is given in the formula sheet that was released before quiz 1.
Okay. So alpha by beta square, only square for beta, denominator. So that is why it will be 1 by 2 divided by 1 by 4 whole square. So 1 by 4 whole square will be 1 by 16, which is in the denominator. So it will go into the numerator. Okay. So these are the messages, is it?
Oh, Smiley has sir posted the link in the chat.
Okay. I thought someone is raising their hands. Okay. Okay, from here we will get the expected value of this gamma distribution as 2 and the variance of this gamma distribution as 8. But we are not looking at the single gamma distribution. We are looking at the sum of gamma distributions. So if one gamma distribution, so that is what we discussed, right? So if x1, x2 to x1 square, x2 square, x3 square and so on, x100 square follow gamma half gamma 1 by 4. Then the sum of this gamma will also follow gamma n times half gamma 1 by 4. So this n here is 100. So it will follow, the sum will follow gamma 100 by 2 gamma 1 by 4. Okay. So you can compute like this, or
So
once you get this,
this thing will be given in exam, or we should know this?
which one?
The
Will follow the
the
gamma.
third line, sir.
These things will not be given. These things will not be given. Sum of gamma will follow gamma. These things you have to know. So sum of normals will follow normal. Linear combination of normal will follow normal. These things you should know. So all these formulas will give you the expected value of a gamma distribution, variance of a gamma distributions, and everything will give you.
Sir, if like the fz of 0.70 we have, like if fz of some larger number is there, suppose fz of 4 is there, 4 point something is there, we should put directly to 0.
0. So that is what someone asked, right? More than 3.5 or 3.6, the answer will almost be equal to 0.
Sir, I have not got this discussion. What is he asking?
So he's asking what will be the value of fz of 4. Okay, capital fz of 4. CDF, or what is the probability that z is less than or equals to 4? It will be almost equal to 1. That is what we are discussing.
Sir, can you please repeat how can we calculate the value fz of 0.7071? In the chart there is a minus 3.4 to 3.4.
If you go below, you will have the positive values also. Okay. So from there you just look at 0.70. Okay. So now you see here, instead of doing this, you can also compute the expected value of this and the variance of this, and it will be 200. Expected value of this will be 200 because 100 by 2 divided by 1 by 4. So alpha by beta. Okay, from here also you can do, or else if you know the connection between a single random variable and this n and mu. So if you know the mu and if you know the 100 samples, then you can do 100 mu, which is n mu, divided by root n sigma. So that also you can do. So if you are worried about how this root n is coming, then compute this. After this, just compute the expected value of this and the standard deviation of this. You are going to get this. The same thing. The expected value will be 200. Standard deviation will come out to be equal to 20 root 2. So you have to subtract 200 and divide it by 20 root 2. So this will follow standard normal. So that is why we have subtracted minus 200 divided by 20 root 2. So now this whole thing can be replaced with capital Z. So this follows standard normal. And this will be standard normal, and the right side part will be 220 minus 200 divided by 20 root 2. So if you simplify it, you are going to get 1 by root 2. The probability that z is greater than 1 by root 2 is 1 minus fz of 1 by root 2. And 1 by root 2 is approximately 0.7071. And we have given the value of fz of 0.7071 in the question. Just substitute that. And 1 minus of that will be the answer. And it will be 0.23885. Okay. So in question 1 and question 2, after knowing the random variable or the function of the random variables, then we have done the same thing. We have computed the expected value of the random variable, standard deviation of the random variable. We have subtracted the expected value and divided it by standard deviation. And we treated the whole thing as will follow standard normal 0, 1. That is what we will do in CLD. Okay. Why we are doing all this is because to approximate the probabilities. So we are interested to find the probability of this. But if you look at the gamma distributions itself, it will be very difficult to compute the probabilities. So that is why we have converted that sum of gammas to the standard normal using CLD. And then we have computed the probabilities. Okay. Let's move. Now, this is a random variable. Okay, Manan Jain. Mananjan, if you are trying to speak, I can't hear you. Okay, try solving this. Let x be a random variable having the gamma distribution. So following the gamma distribution with parameters n and 1. So it is x follows gamma n comma 1. Okay. And we have given you the hint also. If x follows gamma alpha comma beta, expected value of x is alpha by beta and variance of x is alpha by beta square. Now using weak law of large numbers, find the value of n such that this holds. Probability that mod x by n minus 1 greater than 0.01 is less than 0.01. Okay. So in week 7, I hope you guys have gone through what is weak law of large numbers. Can I assume?
Yes, sir.
Yes, sir.
Okay. So the difference between CLT and weak law of large numbers is weak law of large number actually gives us bound, only bound. Okay. It will not give you the approximate probability. It will give you a bound, upper bound or lower bound. So we will predict that using weak law of large numbers. You can say that the probability will be either less than or something or greater than of something. That's it. But by using CLT, you can actually approximate the probabilities. Okay, that is why weak law of large numbers sometimes will not give you a proper bound also. So if your actual probability value is somewhere around 0.23, 0.2 maybe, then using weak law of large numbers, you will get that the probability will be less than 0.7. So that sometimes you may get that using weak law of large numbers, you can you can get a bound that my probability is less than 0.7. Okay, but using CLT, you will get somewhere around it is equals to 0.3 or 0.25. So the difference between weak law of large numbers and CLT is when you want to approximate the probability, you have to use CLT. But when you wanted to just get the bound, upper bound or lower bound, you can use weak law of large numbers.
Hello, sir. Am I audible now?
Yeah, now you are audible.
Yes, sir. So I actually had a doubt in the previous explanation of question number 2. Sir, after the question was being solved, there was 20 root 2 in the denominator. So is there a purpose? Because my connection was lost and I wasn't able to clearly see that. Because 100, if we are taking the variance of for x square, the square root of random variables, the variance is 8. So the answer should be 80, not 20 root 2.
Answer should be
80. That 100 root 100 standard deviation we are multiplying with. So I was
see you are going to get the variance, right? Variance as 8.
Yes, sir.
So what is the standard deviation then?
Okay, sir. Yeah.
Square root of it.
Yes, sir.
So once you do the square root of it, it will be something like 2 root 2.
Okay, sir.
Right? For that is for one random variable. So it's for x1 square.
Yes, sir.
Okay. But we wanted the standard deviation of x1 square plus x2 square plus x3 square plus and so on x100 square. Okay, sum of 100 random variables here. So if each of the following, so if you have variance of x1 as 8 and variance of x1 square as 8 and variance of x2 square as 8 like this, if I look at the variance of x1 square plus x2 square plus and so on x100 square, it will be 100 times variance of x1 or variance of x2, right? All the variances are equal. So it will be 8 plus 8 plus 8 plus 8 and so on 100 times. So it will be 100 into 8.
Okay, sir.
Now you do the square root. You are going to get 100 will come out as 10 outside the square root and square root of 8 will be 2 root 2. So 10 times 2 root 2 will be 20 root 2. Okay.
Okay, sir. Thank you.
Done, sir.
Okay. So just wait for 2 to 3 minutes. So weak law of large numbers comes from Chebyshev's inequality. How many of you know this?
Yes, sir.
Have anyone tried to connect Chebyshev's with weak law of large numbers? Except Smile. Any other? Yes, no, tried, not tried.
No, sir.
Yes,
No.
yes, I had tried once, but if someone tells me to explain it right now, I'll not be able to do that.
Okay.
But I've done it.
Okay. And you have convinced, right? Chebyshev's
Yes,
inequality
yes,
and
yes.
weak law of large numbers are more or less same. So use the Chebyshev's inequality to sample mean minus mu. So x bar minus mu. Or use Markov's inequality to x bar minus mu. So it will be interesting. Try this and come tomorrow. Okay. Come back tomorrow.
Okay, sir.
So just look at Chebyshev's inequality and just look at weak law of large numbers and just try to find what to do with Chebyshev's inequality in order to get weak law of large number. So how the random variables are defined in each of them. Very easy to understand also. So what happened to this? 5 submissions out of 25. Okay, let us discuss in question 3. Let us discuss this problem. And in question 4, I think weak law of large numbers will be replaced with CLT. And we will see the difference between the value of n also. Okay. So what we have to do? They said using weak law of large numbers, find the value of n. Okay. Weak law of large numbers. If you wanted to know how the weak law of large numbers are related, just a second. Okay. So here it is given that x follows gamma n comma 1. And also we have to find n such that the probability that mod x by n minus 1 is greater than 0.01. Just a second, let me see what are the answers you guys gave. 1 lakh. Oh no, 10 lakhs, 1000, 10,000, and 2 of you have deleted the responses. Why so? Okay. So anyway, let's see step by step. First of all, it is given that x follows gamma n comma 1, and we have to find n such that probability that mod x by n minus 1 greater than 0.01 is less than 0.01. Okay. So now what we have assumed is let x be equal to some sum of n random variables x1, x2 to xn, where each of the xi's follow gamma 1 comma 1. So if each of the xi's follow gamma 1 comma 1, then I know that x follows gamma n comma 1. Okay. So now again the x1 plus x2 to xn follows gamma n alpha comma beta. So this sum is nothing but x. So that is actually again equal to gamma n comma 1, and each of the xi's, expected value of xi's will be alpha by beta.
So this distribution I'm not getting. The distribution of x is given to us, right? So it is saying x is gamma distributed with alpha comma beta.
See, what
And
we have done is, okay, we have assumed, or we just let x to be equal to x1 plus x2 plus x3 and so on xn, where this x1, x2, x3, xn are following gamma 1 comma 1.
So that x can represent the x by n can represent the mean of the sample.
N represents the parameter of x, right? So that particular single random variable x, we have treated it as sum of n random variables. So if x is following gamma n comma 1, then each of the n random variables will follow gamma 1 comma 1, because you see the sum will follow gamma n. See, if x1 follows gamma alpha comma beta, and x2 follow x1, x2, xn are IIDs of gamma alpha beta, then sum will follow n alpha comma beta. So alpha and beta we have treated it as
we
one.
have broken it into n random variables.
So now the sum n gamma random variables with parameters 1 and 1. Okay. So from there, each of the random variables expectation is alpha by beta, so that will be equal to 1. And also variance will also be equal to 1, because alpha and beta, alpha betas are 1 for all the x's. Now, what weak law of large number says? Okay. Now, what weak law of large number says? Probability that mod x bar minus mu greater than delta will be less than sigma square by n delta square.
So can you show me the question once more, please?
Yes, sir.
Yes.
Okay, let us do this offline. Yeah, say, okay, on the paper. Okay. So we have been given x follows gamma n comma 1. So what we have done is x, I have taken it as x1 plus x2 plus and so on xn, where each of the xi's follow gamma 1 gamma 1. Okay. So if each of the x's are following gamma 1 comma 1, then x1 plus x2 plus and so on xn will follow gamma n comma 1. So which is actually x is following. So we have just break down this random variable x into n random variable, sum of n random variables, and each of them is following gamma 1 gamma. Now expected value of xi's will be alpha by beta. So here alpha is 1 and beta is 1. So this will be 1. And variance of xi is also alpha by beta square, which is again 1 by 1 square, which will be 1. So now what is weak law of large numbers say? So the probability that the sample mean is deviating from the population mean by some delta will always be less than or equals to sigma square by n delta square. So this is what it says, right? So simple proof for this is we'll discuss this proof also. So if you know the Chebyshev's inequality, mod x minus mu greater than some k will be less than or equals to sigma square by k square. Okay, where this sigma square is nothing but the variance of x. Okay, so this x, and mu is the expected value of x. Okay, so the same thing, replace x by x bar.
Sir, so here instead of taking one random variable, we are actually taking a series of
Sample
random
name.
variables as a sample.
Hmm.
So delta is just k, we are taking it for n samples.
Delta?
So weak law of large numbers is just for samples. It's just an upgraded version of Chevy Chefs. Like
So that is what you just replace x by x bar. So what are you going to get? Probability that mod x bar minus expected value of x bar is again mu only.
mu
Greater than some k will be less than or equals to variance of x bar divided by k square. So what is the variance of x bar? Variance of sample mean sigma square of n. So this is what we have studied, right? Expected value of sample mean is mu, and variance of sample mean will be sigma square by n. So that's it.
Okay, sir.
So this will imply us mu greater than, instead of k they have said delta will be less than or equal to variance of x bar will be sigma square by n divided by delta square, and that n will come to the denominator. That's it.
So I think you have explained it once before, I think. Yes, sir. In a previous lecture, I suppose.
Oh, okay. Okay, anyway, see, this is Chebyshev's, and 2 steps after this is weak law of large numbers. So now you have to use this. That's it. So you have to, we have x1 plus x2 and so on xn as x. Now you see probability that x bar we know, which is x1 plus x2 plus and so on xn by n, minus mu is expected value of this. So what will be the expected value of this? So expected value of x1 plus x2 plus and so on xn divided by n. So this will be somewhat 1 by n of expected value of x1 plus expected value of x2 and so on expected value of xn. So 1 by n of expected value of x1. So x1 follows gamma 1 comma 1, and expected value of x1 is 1.
1. Yes, sir.
So expected value of x2 all will be 1. 1 plus 1 plus and so on 1 n times.
N.
So it
N.
will be 1 by n into n, which will be 1.
1.
So this will be 1 greater than some delta. Okay, delta is less than or equal to sigma square by n. So sigma square, so what will be the variance of this? Which is basically variance of x1 plus x2 and so on xn by n divided by delta square. So this is what we have to find. So variance of this will be 1 by n square times variance of x1 plus x2 and so on xn. So from here variance 1 by n square will be variance of x1 plus variance of x2 and so on variance of xn. So all the variances are again 1. So therefore that will be 1 plus 1 plus and so on 1 n times. So we are going to get 1 by n. So finally what we are going to get is mod x by n. So you see sum is actually x by n minus 1 greater than delta is less than or equals to 1 by n delta square. In the question, if you observe, this delta is given to be 0.01. Okay, so this is given to be 0.01, and we have given that it is less than or equals to 0.01. So 1 by n delta square should be less than or equals to 0.01, and we know the delta value also. So that means 1 by n delta value is 0.01 whole square less than or equals to 0.0. So from here you take n on right side and this 0.01 on the left side, you are going to get 0.01 whole cube is less than or equals to n, which implies n is greater than or equals to 1 by 0.01 whole cube, which is 1 by 10 square. So from here we can get n is greater than or equals to 10 power 6. So n should be 10 lakh almost. So you see, n should be, at least I should have 10 lakh samples to say that that particular probability is bounded less than 0.01. That is what we
So
got.
in the last step where we have found like sigma square by n delta square, after we found its value. Okay, so this in the last, therefore 1 by n 0.01 square is less than 0.01. We just compared it that that equality is less than this and less than this also.
It
And
should
this
be,
is the
see,
maximum bound.
So if my sigma square by n into 0.01 whole square is less than 0.01, then definitely the probability will be less than 0.01. So we have, see, this is true and we want this.
The second one
That
should be,
means,
sir, I think less than equal to. Right.
less than or equal to.
Yeah, that's why you
equal
can
to
say
one.
this is the lowest bound, and other value
Correct.
this will be less than that.
Correct. See, this particular, therefore after it should be less than or equal to.
Yeah. Therefore, I can say sigma square by n into 0.01 square is less than 0.01, right? Okay, good.
Yeah.
Sir, where you would be
Sir,
posting
one
this
show your
PDF?
working, sir.
Where?
Sir,
See,
where?
same place, live session notes.
Okay, sir.
Sir, show me your working once, sir.
My working?
Yes,
the
sir.
same
You
thing,
did,
right?
you did the solution now.
Okay, so the other people do the same thing, but here you have to use CLD. Okay, so use CLD. One second, I will just show it. So the rest of the people try
On
this.
join PD, still it is showing question number 3.
Is it? So maybe your internet connectivity. So it's not question number 3. Just read the hints and everything, no? So the same question, use CLD. There are 4 options also.
Sir, the question is not visible.
Just a second. Let me show her the. Okay, this is my.
Sir, here we have got the variance as 1 by n, right, sir? So the weak law of large numbers is in the right hand side less than or equal to n square by, sigma square by n delta square, right, sir?
No. That sigma square by n is what the variance of x bar is.
That's where my doubt is, sir. Because that n into n is becoming n square.
No. See, that is what.
Yeah.
See, that
Yes,
is
sir,
why
yes,
we.
sir. Sigma square by n is variance. So, yes, sir,
Sigma
yes,
square by n is the variance.
Yes, sir. Yes, sir. Thank you, sir.
Okay, I will just share the.
Can I ask one thing over here? You took gamma 1, comma 1. It's just an example you took, or we got it from somewhere?
No, we have derived it. Like we have let it.
Yeah,
So,
you assumed it. Let this distribution be gamma with 1, comma 1, right?
And I have taken n such samples, and I have added all those n samples to get x, where x follows gamma n comma 1.
Here you took the gamma distribution. We could have taken any other and still gotten the same answers.
See, if you take any other distribution, the sum of those distribution will not sum to a gamma distribution, right? See, here we have given x be a random variable with parameters n and 1.
Yes.
Okay, in order to get n and 1 parameter, I have let my x as sum of n gamma random variables, where each of the random variable is following 1 comma 1 parameters with gamma 1 comma 1. So then the sum will be n comma 1. It will follow n comma 1. Okay. So it's just a small manipulation thing I had.
Okay.
Okay. Okay, you try this CLD, you will get it. Because I wanted to discuss one more question as time is running out. So the same thing, but you have to do the CLD here. That's it. So what you have to do is this. So bring in the Z into the picture. Standard normal into the picture. Okay. Once you bring in, you will get the answer. So you just try it after, and this also is easy. First try this question, 6th question. If you are done with this question, then we can go back again. So what is the 4th moment of the normal 0-9 distribution? Okay. So the hint is basically you should know the moment generating function for normal 0, 9. And once you know the moment generating function, you just look for, so for the first moment, you have to look for lambda power 0 and lambda by 1 factorial. And for the second moment, you should look for lambda square by 2 factorial coefficient, like this. For the third moment, you have to look for lambda cube by 3 factorial coefficient. So similarly, for the fourth moment, you have to look for lambda power 4 by 4 factorial coefficient of.
Sir, can you explain apart from the question theoretically?
Okay. So see, these moment generating functions, why we are studying this moment generating functions? Have you thought of anything like that? So we know the distribution, we have the distribution. For the distribution, we know the mean, we know the variance. Why to study this moment generating function? Basically, MGF.
Yes. Yes.
Any insights of moment generating function?
We can directly compute expected value of x square, x cube, like that.
Okay, expected value of x square, x cube. What are these expected value of x
These
square?
These are random variables for some distribution.
Okay, so these are called moments. So expected value of x, expected value of x square, expected value of x cube, and so on, expected value of x to the power n. These are called as moments. And there is one more term called central moments. So for the first central moment is and the second central moment, everyone knows this, which is the variance. Okay, so like this is called first central moment, second central moment, and third central moment is expected value of x power minus mu whole cube. So like this, these are central moments and these are called moments. So what are these moments is, this is first moment. First moment is mean. So how my distribution is distributed. So what are the possible values x can take? Second moment is, if I look at the squares of the possible outcomes, how the mean or how the distribution, how the expected value is like this. Simply speaking, moments are basically representing the means of powers of the random variable. Like this, first moment, this is the second moment. And this MGF will generate the moments, will directly generate these moments. It will directly give us expected value of x square, x cube, x power n, and everything. It will generate the moments.
This central moments, what is the role of central moments then?
This is another thing. See, the central moment is basically when you centralize your random variable, then computing the moments. Okay. So if you have a sample, looking at the sample or looking at the sample mean.
So centralizing means mean is zero essentially.
Sorry, x minus mu. Yeah. This is not x bar. This is x minus mu. This is x minus mu.
So from there it is mean is zero.
So central moments are basically your random variable is centralized. So once you centralize your random variable, then computing the moments are the central moments. So how do you centralize? You know,
Still means that it still means that being centralized means you're trying to find the deviations from a point, like how much it is deviating from a point. So you have found some central value of that variable and you want to know how much it is deviating from that value, right?
No. See, how do you centralize a random variable? So you will try to get the expected value of that random variable to be equal to 0, right? How do you centralize these things? You know, I suppose. So if it is given like 0,
subtract
1,
the
2,
mean of it, no, sir?
You will subtract the mean of it to the random variable.
Such that expected value of x2 comes out to be 0.
0. Yeah, the first central moment will come out to be equal to 0. And the second central moment will come out to be the variance of x. So this is the variance of x.
Yeah.
Expected value of x minus expected value of x, which is mu, to the whole square. So these are once you centralize your random variable, then compute the expectation of x minus mu, expectation of x minus mu whole square, x minus mu whole cube. So those are called central moments. And simply if your random variable x is not centralized, if any random variable x, your first moment is called the mean, and the second moment is expected value of x square, second moment. So your random variable is having power 2, like this. Third moment will be expected value of x cube, like this. Then this MGF will generate these moments, as well as the most important thing about MGF is it actually defines the distribution uniquely. So if you have a moment generating function, then definitely your distribution is unique. So there is an unique one-to-one mapping between the distribution and the moment generating function. But if you have mean as 10 and variance as 20, so many distributions can have mean as 10 and variance as 20. So there is no uniqueness there. But once you know the moment generating function of any random variable, then correspondingly there is an unique distribution of that random variable. So that is one important thing about moment generating functions. So moment generating functions, so for now this is sufficient. The moment generating function for normal 0 sigma square is actually equals to e to the power lambda square sigma square by 2. Okay, so this is a function.
We have to remember these functions.
See, professor also said something, right? Even though if I woke up you at midnight, you should remember this. But we will give you in the exam but in future, professor intention is in future. You should never forget this moment generating function for standard normal, not the standard normal distribution with mean 0 and having variance as sigma square. And you should know one more thing about in regards of this moment generating function is again expansion of e to the power x.
Yeah, that we know. So x to the power x.
Yes.
Yeah. That is used so many places. Even in Poisson and available it was there.
Yeah. So yeah, Poisson also we have used this. So e to the power x is this. You should know the expansion. And then once you know that, the moment generating function for normal 0 sigma square is this. Now replace x with lambda square sigma square by 2. And look out for, so from here, what we can get is first moment, which is expected value of x, is nothing but the coefficient of x by 1 factorial, or lambda. If you are using the lambda term, it will be lambda by 1 factorial, coefficient of lambda by 1 factorial. Similarly, second moment, if we ask for second moment, which is expected value of x square, which is coefficient of lambda square by 2 factorial. Similarly, if we ask for nth moment, which is expected value of x to the power n, which is coefficient of lambda to the power n by lambda factorial. So this is important in regards of this moments and everything. So if a question need to be asked in regards of moments, this is how we can ask. What is the fourth moment of normal 0, 9?
So you will ask for normal only, no?
Normal or any other. So whichever you can compute the MGF. If we thought that you can compute the MGF, then we can give you.
But for centralized normal, all the odd moments will be 0, right?
All the odd moments will be 0. Correct. So what if it is not centralized? Anyone thought about this? So what will be the MGF of?
Not centralized.
With mean mu, not 0. So what will be the MGF of this?
Well, so expected value will shift. Like if we talk about first moment, it will shift by mu only. So.
Okay. So let me give you. Try to prove this.
So lambda mu plus the normal one.
So this is nothing but e to the power mu lambda will be multiplied. Okay. So if this mu is 0, this term will vanish. It will become 1. So the standard normal 0 sigma square will be this. But if it has mu also, this is how the moment generating function will look like. Okay, but it is not necessary now. Now try to solve the fourth moment. Solve the fourth moment of the normal 0, 9 distribution.
No, match 2 class is there. Can I release that?
Yeah. Please. I'm done. Mostly I'm done. So let us see whatever I discussed. I think 243 is correct. So we have to look out for the coefficient of lambda to the power 4 by 4 factorials coefficient. So that is what we need. So we have given the sigma square value. Sigma square is 9, which is 3 square. So similarly, you can get the moment generating function for normal 0 3 square. It will be e to the power lambda square 3 square divided by 2. So use the expansion of e to the power x. It will be 1 plus lambda square 3 square by 2 plus lambda square 3 square by 2 whole square divided by 2 factorial, like this.
Sir, after this one, show the question number 5 also, sir.
I will show.
Thank you.
So
Sir.
now you see, here we got lambda to the power 4 into 3 to the power 4 divided by 2 factorial into 4. So we want the coefficient of lambda to the power 4 divided by 4 factorial's coefficient. So what I have to do, I have to multiply 3 in the denominator and numerator. Then I will get 3 power 5 by 4 factorial. So from there I will get the coefficient of lambda to the power 4 divided by 4 factorial's coefficient will be 3 to the power 5, which is 243. Okay, like this you can solve. So even you have a question in graded assignment also, just try to solve that also. So that is how you solve. And the question number 5 says, suppose speed of vehicles on a particular road are normally distributed with mean 25 and standard deviation 3. Okay, miles per hour and miles per hour. So units will not play any much role. So don't worry about units. So just to make that question contextually correct, we will just give you the units. So the speeds are given to be normally distributed. You see in week 7 and 8, usually whatever the question you see, we will always give you the mean and the standard deviation of the distribution. So here we said speed of the vehicles are normally distributed with mean 25 and standard deviation 3. What we ask you is find the probability that the mean speed, which is the sample mean, the mean speed of 30 randomly selected vehicles is between 24 and 27.
We will use CLT, sir, right?
You have to use the CLT. See, find the probabilities. So whenever we ask you to find the probabilities, you have to use CLT only. Using weak law of large numbers, we will never find or approximate the probabilities. We will only get the bounds for probabilities. Okay. If we have asked you for bounds, then only you have to use weak law of large numbers. If we ask you to find the probabilities or we should have said that approximate probability. So find the approximate probability that the mean speed of 30 randomly selected vehicles is between 24 and 27. So how will we do? We know that x bar is nothing but x1 plus x2 to x30 divided by 30. So which is the sample mean. So compute.
We are just standardizing the x bar, right?
You have to standardize the x bar. So compute the expected value of x bar and compute the standard deviation of x bar and subtract that from x bar divided by standard deviation. And you have to do for 3. So you have to do for 24. So you have to subtract 24 minus expected value of x bar divided by standard deviation of x bar is less than, it will turn out to be standard normal z, less than 27 minus expected value of x bar divided by standard deviation of x bar. Okay, so if you do so, you will get the answer.
Yes.
Okay, then that's it about today's session.
Sir, I have one doubt. Sir, what if in this question we are asked to find the third moment?
A third moment will be 0, right? If there is no lambda cube in your moment generating function, then that will be 0.
Okay. Okay, sir, got it.
Okay, so what am I doing is I am turning this on student paste. So once if I turn this on to student paste activity, so you can shuffle this, shuffle the slides. Okay. So I turn this on, and also I will give you the link will be given as it is, and also the slides will also get uploaded. But if you wanted to do it right away, if you want the slides right away, you can use this link. So this, whatever you have opened, you can toggle between the slides. So you can check now itself. You can directly toggle between the slides and you can directly look into the solutions of everything. Okay.
Yes, sir. Got it.
Thank you, sir.
Okay. Okay. Thanks a lot and have a good day.
Thank you,
Thank
sir.
you,
We
sir.
cannot download from there.
Good night.
Where is the link? How to toggle, sir, between the slides?
You
left
can
and
toggle,
right.
just go to that page. You can see, you can toggle between different slides.
Sir, can you stop the recording? I am not even able to leave the class. I'm co-host.
Okay. So I stopped the recording. Just a second. I will stop the recording.